All right, I'm going to blow through this really quick. These are the notes that I did in class, and I just want to do a quick audio over them because the audio did not come up last time, or in class. All right, so the first thing I pointed out to the class was that these are some integrals that we should know how to do coming in. This one right here, we've got basically a linear term on top. On top we have a quadratic, but this quadratic just has x squared and then a number. So there's no x term, it's an x squared term, and then a constant. If we have something like that with addition, or it turns out subtraction, doesn't matter. There's a formula in the back of the book. If it's addition, it's this formula. If it's subtraction, just go look in the back of the book, you can find it. So generally speaking, we know how to handle integrals with constants over x squared plus or minus a constant. In this case, again, the arctangent is the formula. Now, we also know how to handle if we have, instead of a linear I said linear up here. Yes, by that I meant constant. Sorry. We also know what to do if we have a linear expression up top, but it has the variable x in it. So if we have x by itself up top, then in the bottom we have our quadratic with x squared and a number, and addition between them. Then we can just make a substitution, just a basic substitution, and we'll be able to work the integral out, which I showed up here. I'm not going to work it out. So generally speaking, again, if we have x on top and we've got quadratic on the bottom without an x term, we should be able to handle it. Now, if we have a constant on top and we have a quadratic on the bottom that does not factor, so you cannot factor this, then what we do is we have to complete the square. And then once we're here, this kind of looks like u squared minus a constant squared, and we have a formula for this. Now, if this quadratic on the bottom does factor, and we have a constant on top, then what we can do is we can factor the bottom, and then we use partial fractions. So this was just a quick overview of the things we should have known going into class that day, yesterday. All right, next slide here. The question, one of the big questions for the day was, okay, well, how do we handle something like this? If we have a constant on top and we have a quadratic on the bottom, and this quadratic is something that we can or cannot factor, how do we deal with this? So if it's something that factors, we use partial fractions. If it's something that doesn't, we complete the square. So, you know, again, sorry, I kind of misstated that. That's kind of what we already knew coming into class today. We know that we can handle constants over quadratics. But this is different. Okay, so for something like this, the fact that we have an x in the numerator causes all sorts of issues because we can use partial fractions, but when we do that, it's going to require multiple steps. It's not going to be just a clean problem, I should say. So I did this problem, I think, in class right now. So let me show you that. Okay, so the first thing we did, because this does not factor, is we completed the square. So I took that quadratic, I took the -4, I took half of it, and then from that got this. And then the technique for completing the square is take half of the coefficient of x, then square it, and that gives you 4. Then what you do with that 4 is you use that 4 and you rewrite the quadratic and you add a hidden 0 in here. So I'm going to add 4 and take away 4. The first 3 terms of this quadratic are guaranteed to factor, and here's what it is. And then you put these last 2 together and you get this. So that's our completing the square. So now we have this integral instead of the one up here. All right, now at this point, I told the class there were 2 options. Here's one option of making a substitution of u equals x minus 2. So I'm going to use that as my substitution. And therefore, this x will be replaced with u plus 2 because I can just take this equation and solve it for x. And then du is dx. So when I rewrite the integral, I get this. The x is here, this is u, and then here's our minus 2. And then du, of course, is dx. Now this integral, I can take this integral right here, and I can split it into 2. I can take the u over the denominator and then the 2 over denominator. If I take the u over the denominator, this integral is just a basic substitution problem. So w equals u squared minus 2. Do that, you work it out, you get this. right here. And then on this one, we use formula number 20 in the back of the book, with this 2 being a squared. So a squared is 2, which means a is square root of 2. And then using the formula in the back of the book, I get this. And then on the next page, I replaced w with u squared minus 2. And then I replaced u with this up here, x plus 2. Or sorry, x minus 2. So I do that on the next page. So here's my w becomes that, and then my u becomes that. Here my u, and then my u. And that's it. So that's how we deal with that integral. Now I show the class a different way of approaching the same exact problem. And I think what I'll do is I'll erase this so you can see it. Okay, so starting out with the original problem, I said let's just act like we would really want to try and force that to be our u. So here it is right here. Then the derivative of that is this. And so I really would like to have a 2x minus 4. So what I do here is I'm going to make this happen. I'm going to multiply my x up here by 2, but I can't do that unless I multiply by 1/2 out here. So now I've got 2x, so I'm happy with that. Now I need a minus 4, so I come in here, I subtract 4 and add 4. So there's a hidden 0. So here's my new integral. And now I split the integral right down here. And I create two integrals. It'll be this over the whole denominator. That's this one. And then the 4 over the entire denominator. That's this one. This first one is guaranteed to work because the way I designed it, I know that the bottom is u and the top is du. Or in other words, it's 1 over u du. And so the antiderivative is natural log of u. And so here's the answer. Now in this integral right here, we now have a constant on top of our quadratic. And so what we can do is we can complete the square like we did before, and then from there go straight to our formula. Formula number 20. So either technique, the one I showed before this or this one, work. The class said that they preferred this one. All right, let me see what we did next. Okay, so here was a new problem. Gave them this right here. First thing we noticed that the degree of the numerator was equal to denominator, so we had to do long division. So here's the long division. I'm not going to work through it. And so we got this. And then from there, we said that gives us two integrals. So antiderivative of 1 gave us x, and then the antiderivative of this is right here. Or sorry, not the antiderivative. That one we have to find the integral of. So that's why I still have the integral sign here. And then if I take away this, you can kind of see what I did here. Again, I forced the denominator to be my u, so that forced this to be my du, which means I had to come in here with an 8, and I multiply the top by 8 and the bottom by 1/8. That'll give me my 8x, but that 8 must distribute through. So that's why on the next line, or the next integral, I have an 8x minus 8. And then from that, I needed a minus 4, so I took this over here, and then I said subtract a 4 and add a 4. And that would allow me to get the 8x minus 4 by itself, which is right here, and then these two together, which is negative 4, I went ahead and put that for its own integral. But 4 minus 8 is negative 4. Negative 4, if I take it out of the integral and multiply by 1/8, I got negative 1/2. So really, this number over this denominator, I simplified it out to come up with this. So now on the first one, again, it's a natural log. And then on the second one, we're going to have to complete the square. So in completing the square, I told everyone to remember that you cannot have a number other than 1 in front of x squared. So we start here. The first thing we do is we take out a 4, which is here. That gives us this. Then I take the number in front of x, which is negative 1. I take half of it. That's this. Then I square negative 1/2, which is this. And I add and subtract it. So on the next page, I do just what's in that integral. Actually, I wind up taking that 1/2 with me too. So let's go take a look at that negative 1/2 with that new integral written with completing the square. So here's the integral I'm working on. Here was my completing of the square. I had my two numbers. I add the 1/4, subtract the 1/4 inside that parentheses. The first three terms factor to be this. These two together give me the 1/2. And then I go ahead and I put this expression right here back in for this. And when I do it, the 4 on the outside, just pull it completely out of the integral and multiply it through on the bottom, which gives me the negative 1/8 instead of negative 1/2. And then from this is basically the form u squared plus a squared. So that's an arctangent, and I didn't work it out. I just showed everyone, that's the formula you would use. All right, what else did I do? Okay, then we did this problem. All right, so this one's a mess, but we look at this problem, we notice that the degree of the numerator is 3. Degree of the denominator is actually 5, because if you took this and squared it, you would get an x to the 4th, and then multiplying through by x, you get an x to the 5th. So I know that the degree of the numerator is less than denominator, so I don't need any long division. And then we use the fact that anytime we're going to use partial fractions here. So anytime we have a linear factor in the denominator, I put constant over that linear factor. And then this was the new thing that we learned in class. It was that if you have a quadratic factor, which is this, that is not factorable, so we cannot factor x squared plus 1, and it's repeated, then here's what we do. We write down the quadratic factor that can't be factored, and we put on top of it, instead of just a like this, we put a linear term on top, so bx plus c. And because it was repeated, squared, we have to write it again, this time the power coming up to 2, and then another linear factor or linear expression on top, using different letters. And I may as well show you this because I don't want you to get too lost with this. That comes from this page on the previous class. It said that if you have a quadratic that can't, it says if you have a quadratic that can't be factored here, then you're going to write that quadratic with something like this on top of it. If you have a quadratic factor that can't be factored and it's got a power, then you've got to do the quadratic factor with something like this on top, and then you keep doing it and bringing the power up, and you keep doing that until you get to the final power. Now in our problem, we only had a squared here, right? Our power here was squared, so that's why I only needed to do to the first power here and then to the second power. Then I multiply through by the LCD. That's this line right here. I multiply everything, both sides of this equation, by the LCD, which leaves me with all of this. Then I expand all this out. So I multiply it all out, and I'm just going to leave that to you. And then we start matching up like terms. So I get all my x to the 4ths together, x cubes, x squareds, x's, and then numbers, or letters by themselves. Then I factor out an x to the 4th. On that one, cx cubed, I don't factor anything out. On these three, I factor out an x squared. On these two, I factor out an x, and then the a I leave by itself. Then what I do is I match up each of the letters here, or coefficients, to what's on the other side. So the number by itself, which is a, should be a 1. The number in front of x, that's c plus e, should be equal to the number in front of x here, -1. This in front of x squared, 2a plus b plus d, must match what's over in front of x squared here, so 2. The c in front of x cubed should match this, so -1. And then since there is not an x to the 4th over here, these two have to be equal to 0. And from that, you can create these, 5 equations. The first one is this one. The second one is this. The third one is this line. And then this is this line, and then the a by itself is this. So what you get then is a matrix, which is over here, and then you go into your calculator, do RREF. And when you do that, you get your answers. So now we got our answers off the calculator, and then we go back and we plug all those values in, A, B, C, D, and E, back into, where the heck was it? Right here. We know that that integral should turn into this, right? If we put an integral sign here, integral here, that means integral of all these. Replace all those a, b, c, d, and e. Here they are. We get this. The first one is 1 over x. This one's here, I factor out a negative. This one is just x over x squared plus 1 squared. This first one is just a natural log, right? Natural log x. This one is going to be a quadratic that can't be factored with a linear expression on top. So I suggested split this into 2. This first one is a basic U substitution. The second one is a formula for arctan. For this one, basic substitution, U is x squared plus 1. It should work out. All right. Hope that makes sense. And you know what? That was the last page. So that's what we covered. I thought we had more than that. Oh yeah, we did. Okay, then I started talking about improper integrals. So I started talking about, okay, the area under a curve between A and B is basically this formula. And I said, well, what if we, instead of stopping at B, what if we go out forever? So the integral becomes something like this. You go from A to infinity. And that means that you have to find the antiderivative, then you have to plug infinity in, then plug in A. And I stressed to everyone you can't plug in infinity because infinity is not a number. But when you see infinity inside of a function like this, what you're really saying is take the limit as you let that value, we'll just call it x, go to infinity. And then we could also look at an integral where instead of having a left endpoint, we could go out forever in the direction to the left, so to negative infinity. So this is what the integral would look like, negative infinity to b. Then, let's see. I said, well, there's no sense in, we could go out to the right forever or to the left forever, or we could do them both at the same time. If we do it both at the same time, this is what your integral looks like. So the idea here is that we don't necessarily have to have endpoints on our integrals anymore. They can go out to infinity. All right, so let's see what example I had here. This first example, find the basically the area under the function 1 over x from 1 to infinity. So here's the function, start at 1, go to infinity, that goes out that way. Find that area. Well, if we do that, we first find the antiderivative of 1 over x, which is natural log of x. Then we take infinity, plug it into natural log, that's here. Then we take 1 and plug it into natural log, that's here. Natural log of 1 is 0. Natural log of infinity really means what's the limit as x goes to infinity of natural log of x. And so I drew the natural log function over here to show you that as you go to infinity, that means as you start moving to the right forever, this function starts to grow. I mean, it's growing, it's slow, but it is going up. So it is approaching infinity. Oh, that's not infinity. That's infinity. So it is approaching infinity. So what you get is infinity minus 0, which means it's infinity. What we say whenever we get an answer like that is that this integral right here diverges. All right, and I talked a little bit about sine. Don't worry about that. Okay, then we did another problem. I said, okay, now change it. Make the function 1 over x squared instead of 1 over x. So here's what it looks like. We want the areas. We go out to the right forever. We take the antiderivative. Here's the antiderivative. We plug in infinity here, and we get this right here, and then we subtract from it what we get when we plug in 1. On this first one right here, we have the idea of really what's happening as we let that denominator go to infinity. So what's the limit as x goes to infinity of negative 1 over x? So we have basically a fixed number on top. We have a number on bottom that's becoming infinite. That thing goes to 0. That's a Cal 1 problem. So this goes to 0. Over here we just get negative 1, but then we're subtracting it. So negative 1 minus 1 is 1. So the area is 1. In the case that we get a constant like that, we say that this integral is convergent to 1. And then the last problem, I believe this is the last problem I did. Yeah, this one was it. We said let's try and find the integral from negative infinity to 0 of x e to the x. So the first thing we had to do was find the antiderivative, which I didn't show, but there it is. And then from that, we got to plug in 0 and negative infinity. Plugging in 0 wound up to be pretty easy because 0 here gives us 0, so that kills that whole thing. And then e to the 0 is 1, so minus 1. So that's this. This was the part that was tough. So I did all the work below. We're going to plug negative infinity into this. So I said, all right, well, that's the same as saying what's the limit as x goes to negative infinity of that expression. We said, well, this goes to negative infinity. E to the negative infinity is the same as 1 over e to the infinity. That's a fixed number over something that's getting huge. That goes to 0. And then this one right here, minus e again to the negative infinity, goes to 0. So this was the part that caused the problem. We have 0, right? Negative infinity times 0. And that's an indeterminate form. You cannot tell what that answer is. So what we did is we factored out an e to the x. we said, okay, now I let x go to negative infinity. We already said that that goes to 0 from this right here. And then this one right here goes to negative infinity. So we have this indeterminate form that we can't tell what's happening. And whenever you have 0 times infinity or 0 times negative infinity, you take one of these, your choice, and drop it to the denominator. So I chose to take the e to the x and drop it down, which made it turn into e to the negative x. And now when you let x go to negative infinity, you get negative infinity over positive infinity, and that means you can use L'Hopital's rule on that. So I believe I do next page. Oh wait, do I do it? Where is it? Where the heck is it? Oh, here, it's over here. So take that, do L'Hopital's rule, which means derivative of top and bottom. So derivative of top is 1. Derivative of e to the negative x is negative e to the negative x. So what's happening is on the bottom, or let me do this a little slow. You have 1 on the top. On the bottom you have e to the negative infinity. Negative and negative is positive, so this right here is really like an e to the infinity. And so the top is fixed, and the bottom is getting huge. Now it's negative, but it's a huge negative number. That thing's going to go to 0. So we were able to come back up here and say, all right, this side right here, when we plug in negative infinity into this, we get 0. So the answer to our problem was just -1. And we talked about why would it be negative. That's weird, but it's because part of the graph of this function is below the x-axis. So, you know, your answer is represented as a negative number. That's it. Hope that helps.